Hi, this video is for 2.4, part 2. Continue with the topics of continuity. Last time we talked about what is the criteria of showing that a function is continuous at a point, the two conditions, and also we look at how to determine if a function, piecewise function, or any function is continuous or discontinuous, and also name some discontinuous name. Okay, so the last things that I didn't mention in the last things is what we talk about continuity in a point or discontinuous at a point. And here we can also talk about continuity in an interval. So a function is continuous in an interval if it is continuous at all the points. And in the book, we actually show that for sine and cosine function, they are continuous at all points. And you can kind of, common sense look at that sine and cosine function that always continues like a periodic function, right? Just the wave, the sine and cosine wave go on and on forever. So there's no breaks or whatsoever. So it is a continuous function in all the domain. Then this particular fact allows us to do some very good limits. Okay, so going back to evaluate limit. If I want to do sine of a polynomial, like 2x or 4x, or even such as sine 6x, or sine x squared plus 1, or sine x over 2. So later on we'll run into this kind of function. So how can we do limit? Because this the limit law only allows us to do polynomial and rational and root, but doesn't allow us to do these kind of things. It turns out that if sine is continuous, that means this composite function theorem shows that if f of x, the outside function, is continuous, and the inside function has a limit of L, you're not supposed to do it inside, but if you just outside of the case, just do the inside function, it has a limit is equal to L, then we basically can do f of L. That would be the limit. Okay, so this is called the composite function theorem. It applies to sine, cosine, all the trig function, as well as later on like log function and exponential function when we talk about those. So since trig function are continuous over all the domains, so we can do continue to use direct substitution to find limit of sine of a polynomial or rational, is provided that that particular limit exists. Okay, so let's say we want to find limit x approaches by sine pi x. So we can all of a sudden do limit just pi x and move, kind of like switch this because this is a composite function. The inside is pi x, the outside is sine, and then do the sine outside. Okay, it's the same as doing the sine first and do the limit of the polynomial inside. So this is a polynomial that is equal to 5 pi. So the limit is actually sine 5 pi, which is the same as sine pi because of coterminal angle. Sine pi is what? Sine is here. My y coordinate is 0, so it's equal to 0. So this is one use of the fact that sine and cosine are continuous, and you can, if they continue, you can do the composite function theorem to do limits. Another theorem that is very useful is intermediate value theorem, abbreviated as IVT. Intermediate value theorem is a theorem that is used to prove other theorem in calculus, ultimately prove the fundamental theorem of calculus. So by establishing continuity these topics, we can prove the intermediate, or we can use the intermediate value theorem. We don't prove it here. If you're interested in the proof, you can go back to the book and look at the proof. So this is just telling you the result of the continuous intermediate value theorem, and also what it is useful for. So in a nutshell, it's useful for us to determine if there's a solution to a function. Okay, so what happens is if I have let's say this, look at this graph, f of x is continuous in this interval from a to b. The closed interval starting from a to b is all continuous. No breaks, no jump, very smooth. It can fluctuate up and down, but f of a would result in the function f of a. So this is f of a. It's very small. B will result in the function value f of b. Then in between f of a and f of b, can remember between this, only these two, not, they might go over. So between a and b, f of x might go over, but we don't care. We'll just look at this range. If you pick a number c, there must be a solution where f of c is equal to z. You must be able to find a solution c here, so that when you function from the function of c would equal to any value in between here. Any number you pick, you can pick one that is very close to a, you can pick very close to b, but you should be able to find a number that satisfies this, that you can map this c to z. Okay, so okay, let's do the first example. Suppose f of x is continuous. Of course, I didn't specify it. F of x is continuous in the interval 0, 2. In this, we know it's continuous. And then f of 0 is 4. F of 2 is 10. So you can imagine the graph being like this. Okay, so this is 0. I have a 0, 2. It's 4 here. And then the other one is 2. But it maps to 10. Okay. So I have a point here. So my function can go up and down. It can go really up and really down. But just between 0 and 2, the function is 4 and 10. So can we say that it has a 0 in the interval from 0 and 2? Now, so because 4 to 10, just guarantee that from z in IVT, just guarantee that from c is from 4 to 10, we can find f of c equal to z. But z is not a 0, right? These are just from 4 to 10. C is in 4 to 10 only. So which is not 0. C does not include 0. So we cannot guarantee that there is a 0 between 0 and 10. So it will be a no. Okay. So unless you have the other f of a is including 0, then it is not. Now this is the second case. F of 0 is negative 4. Okay, so your f of 0 is a negative 4, but your f of 2 now is 1. So this is a 2, 1 here. And you look at this. So these are all your choice of z that you can get. So that f of c around here would map to it, because you would imagine that earlier you imagined these go like this only. This you have to go through. Can you avoid going through 0? You cannot. They have to go through it at least one. You can actually jump back and forth multiple times, but there must be one. So you will say yes, because of IVT, intermediate value theorem. 0 is between negative 4 and what? Negative 4 and 1. This is 1. So there must be a c, so that f of c is equal to 0. And this c is between 0 and 2. Okay, so that's the use of IVT. So another example would be, actually I know what the function is, and we have to check that they have at least one 0. That means I can find f of x that's equal to 0. So let's plug in f of, so the hint is say, plug in f of 0 equal to what? So 0 minus cosine 0. Cosine 0 is 1, right? So 0 minus 1 is negative 1. What is cosine pi over 2? Cosine pi over 2 is pi over 2 minus cosine pi over 2. So that is pi over 2 minus 0. That is pi over 2. So this is a negative. This is a positive. I have the function in the function value. 1 is negative 1 the other is pi. So 0 is between them, right? 0 is the z, right? It's between -1 and pi over 2. So there must be f of c equal to 0. So that means one zero must exist, at least one zero. You cannot have the function that goes past from -1 to pi without cutting through. At least one zero. The zero must be between 0 and pi also. So that I have, so this particular question we'll do it in class. This we'll do it in class. And that is all for 2.4.